In the work we've done so far in this course, we've really focused on right triangles. So having a triangle with a 90-degree angle. What we're going to be looking at this week are oblique triangles. So these are non-right triangles that we'll be looking at. So non-right. So as we can see down below here, we have this triangle, and really we're focusing on this kind of outside of the triangle. Within there, we do have these kind of two right triangles coming through, so that's something we can use to start using our sine and cosine. But overall, what we're trying to do is we're going to end up solving all of the side lengths, all of the angle measurements for this oblique triangle. Something we want to keep in mind is that sine, cosine, tangent, like everything we did with SOHCAHTOA, was specifically for right triangles. So that'll be kind of a hard habit to break, but it is part of our work here. So, law of sines. What we're going to do is look at this triangle and we're going to say we know what alpha is, so this angle measurement right here. We know what beta is, this angle measurement right here, and we know this side length A. So if we know those three pieces, can we find this value for B? So we're going to kind of play around with this and solve until we kind of find the law of sines. Just so you know the notation here, we're going to be using this kind of general notation for our triangles where you'll have an angle alpha, and then opposite of that angle will be A. We'll have an angle beta, and opposite of that will be side angle or side length B, and then angle gamma, and opposite of gamma will be the side length C. So we'll kind of have these pairings of angles with their opposite sides. All right, so let's say I wanted to evaluate sine of alpha. So alpha is us standing right here, and if I wanted to evaluate sine, so that's my opposite over hypotenuse, and like I was saying, is sine only works with our right triangles. So what I'm doing is I'm visualizing this right triangle right here, where my opposite would be H and hypotenuse would be B. So sine of alpha, we would have this height of the triangle H over that side length of B. Now what I'm going to do is just rearrange this a little bit to solve for H, and doing that I would just multiply both sides by B, so that's coming from a B times sine of alpha. So we have that relationship there. Now what if we wanted to do the same thing but with beta? So let's say I'm at this angle beta and I want to look at sine. Now, again, I'm focusing on a right triangle, which is what we have right here. So I'm focusing on this triangle right here. Oops, everything closed down 1 second. Okay, we're back. So I'm focusing on this right triangle right here. So with that, H would be opposite again, but now my hypotenuse would be that long side length of A. So that would be the hypotenuse right there. So sine of beta, we would take opposite of H divided by hypotenuse, which was the side length A. Again, I'm just going to solve that for H, multiply both sides by A, so that'd be an A times sine of beta. So we got these two relationships out overall on this large oblique triangle, but with that we could visualize these right triangles that come through by mapping out the height of the triangle. So we get these two relationships. We have this relationship is equal to H, this relationship is equal to H, so what we can do is just set those equal to each other. What I can do is say B times sine of alpha is equal to A times sine of beta. Now that's great right there. What I'm going to do is move things around a little bit to try to match up those pairings that I mentioned before, that idea of like alpha and A working together, beta and B, this kind of pairing of angle measurement with this side length opposite of it that goes across the triangle. So what I'm going to do here is kind of match up those pairings. I'm going to move A over to this side, and to do that what I would do is divide both sides by A, And then I'm going to do the same thing with B. I'm going to bump that over there. So essentially what I'm going to do is I'm going to divide both sides by A times B. So on the left-hand side, that'll get B to just cancel out, and then I'll have that grouping that I'm looking for with alpha and A working together. So that'll be that we take sine of alpha divided by A, and that's going to be equal to, and then on this right-hand side, the A's would cancel out. So we'd get that pairing of beta with B, so sine of beta divided by B. So this is starting to form our law of sines. It creates these ratios that are equivalent of each other, that if you take the sine of one angle measurement and divide it by the side length that's opposite that angle, it's going to be equal to sine of a different angle measurement on the triangle divided by its opposite side length. And the same is true with gamma and C. The same ratio occurs. So what our law of sines looks like is that for any oblique triangle, so if I have some non-right triangle like that, and we have alpha and side length A, and we have beta and side length B, and we have gamma and side length C, then if we want to work with values on this triangle, what we can do is take sine of alpha, and if we divide that by A, that'll be equal to sine of beta divided by B, which is equal to sine of gamma divided by C. Now, we only ever use two of these at a time. It'll just depend on what information you have. So what you'll do is you'll pick two, essentially. You'll usually have one where you have all of the information. You have an angle measurement and its side length, so that would fill in enough to give you a number on that side. But then maybe you have one unknown, and maybe it's happening with B, or maybe it's happening with C, so then you would just fill in the blank with that. So what we'll do is go through a quick example with this as well. Just so you know when to use law of sines, what we're going to do is have this wording for kind of what we know about the triangle. So we'll be given these oblique triangles and just given part of the information. So one case would be angle, angle, side. So what that would look like is if we have our oblique triangle, in some form or another, they give us one angle, they give us the next angle or an angle next to it, and one side length. I'll just put a 1 there. So it's kind of like if you're reading around the triangle, it goes, we have an angle, angle, side. So that's where angle, angle, side comes from. Angle, side, angle could look pretty similar. It's just the side length that we know would be happening in between the two angles. So we'd have that first angle, we'd have that second angle, and in between, we'd know that side length. So if we're reading around, it's like we have angle, side, angle. And then our last case here is angle, side, side. So if I have my oblique triangle, is that if we know an angle, and then we know a side, and we know a second side. So angle, side, side. Now this one at the end here is also called the ambiguous case. So we're going to be talking about this one quite a bit in future videos here. And it's because sometimes this could lead to a triangle that actually doesn't work. Sometimes it could lead to actually two triangles working. There can be multiple solutions, or one solution, or no solutions for this case when we're just told about an angle measurement and the two sides next to it. So we need to be careful with this one, and we'll go into more detail with that. We're going to jump in with some examples with angle, angle, side, and angle, side, angle. All right, so let's look at an example and see how we use this law of sines. So here we have an angle alpha. Here we have an angle, that's our gamma right there. And then we have our side lengths. They're opposite there, like this would be B. And let's see, we want to solve the triangle. So basically we want to find A, C, and beta. Now, usually what I do with these is I first look at the angle measurements. I kind of start on the inside because we have that nice rule that all three angles should add up to 180 degrees. So what I would do is check out the inside and see what we know. Sometimes you'll only know one of the angles, and with that, we'll have to jump into law of sines or eventually law of cosines to help out. In this case, we know two of the angles, so what that tells me is I can immediately solve for beta. And what we would do is just take 180, take out the 98, take out the 43, and that would give me that beta is equal to 39 degrees. So I could go ahead and fill in the blank there, or just having beta equals 39 degrees in our work there. All right, and from there, we get a little stuck, because what we need to do is find some side lengths. So we're going to end up with two rules at the end of this week. We're going to have law of sines and law of cosines. And while I specify which cases work for which, really you can end up just trying to plug into either. And I typically start with law of sines. So what I start with for looking at law of sines is I try to look for one of those pairs, an angle with its opposite side length. So I see I have 98 degrees, but I don't know A, so that's no good. 43, but I don't know C, so that's no good. 39 matched up with 22, that's fantastic. So what I could do is fill in one of those ratios. So taking sine of 39 degrees, so sine of beta, divided by that side length of 22, and then equals. And then what I'm going to do is just figure out which side length I want to solve for first. I'm only choosing one. I'm not doing these all at the same time. So I'm going to go ahead and I'll just go alphabetical. Let's say I want to start with A. So what this will look like is I'll take sine of, and then the angle that's opposite of A, so alpha, 98 degrees, over our unknown A. So we end up with an equation where we just have a single unknown. So the fact that we can set that up is a clear idea of we're using law of sines. If we tried this and we couldn't fill in enough information, eventually that's when we'd look at trying to use law of cosines instead. All right, so if I wanted to solve for A here, there's a few ways to go about this. I'm going to think about cross multiplication. So that's where you multiply across the equal sign. So like on one side of the equation, I'll have the sine of 39 times A. So I'll have A times sine of 39 degrees equals 22 times sine of 98. Now taking sine of these values, I would try to make them exact. If I could evaluate them using the unit circle, I would. That doesn't work in this case. So we're going to end up in a calculator here. I'm going to divide both sides by sine of 39. So A is equal to 22 times sine of 98 degrees over sine of 39 degrees. And this is where I need a calculator. So in this section, we're working with triangles, which means we're going to be in degree mode. Unless it specifies otherwise, we're going to be filling in these measurements with angles, or rather in degrees. So with that, when we go to our calculator, make sure you're in degree mode. And I'm just going to type in, and if you can set up the fraction beforehand with this A over B, 22 sine of 98 over sine of 39. And there I get this 34.6181. I can round that to a 34.62. And that'll be a length, which we don't have any units, so I'm just going to leave it as 34.62. So I just found there is this side length. Now, I have one more side length to do, and a very common thing that students do here is they go to the Pythagorean theorem. However, that is not allowed. We cannot use the Pythagorean theorem here because the Pythagorean theorem only works with right triangles, which means we would need a triangle with a 90-degree measurement in it, which we do not have. We do not have a right triangle here. So this whole section will be these oblique triangles. So Do not use the Pythagorean theorem with these. With that, we have to go and do this all again. But instead of working with A and alpha, now we're going to be working with C and gamma. So I'm going to take that same kind of ratio that I set up there. So that's sine of 39 degrees over 22 equals, but now I'm going to use C and gamma, which gamma was 43 degrees. So I'm taking sine of 43 degrees over C. And then I'm just going to solve for C, so I know what to plug into the calculator. So C times sine of 39 degrees is equal to 22 times sine of 43 degrees. Divide by 39 degrees, so I'm getting a 22 sine of 43 over sine of 39. Sorry, lost it there. All right. So with that, we're going to go to our calculator. I'm going to have, and you could just, actually we could just edit it there. What, in the numerator, we're just changing that to a 43. So that's a 23.84. So with that, I'm going to go over here and 23.84. Now, with the triangles, and especially when we draw the triangles, they're probably not going to be to scale. I would say typically they're not to scale. But something I do to kind of check out if I'm even on the right track with the solutions is there is this relationship between the angle measurement and its opposite side length. So like if I look at alpha is 98 degrees, and that's the largest measurement of the other angles. And if I look at the side length across from it, it should match up with the longest side length. So 34.62 is longest, so that's perfect. 43 degrees is second largest, and that gives us the second largest side length. And the smallest angle will give the smallest side length. So there will be this relationship between large and small with the angle measurements and the side lengths. And really that's what I use just to kind of check to see if my numbers are on the right track. And that if that doesn't line up, then I would maybe double check my arithmetic over here.